Hi, welcome back to the Materials Research Laboratory Scanning Electron Microscopy Orientation seminar. This is part 2. This part we will start with the interaction between the electron beam and the specimen, as well as its effect on spatial resolution. As mentioned earlier in part 1, the electron beam will interact with the specimen, and there will be various signals generated during this interaction. These signals include OJ electrons, which is the signal used in OJ electron spectroscopy, and we are not going to cover this in this seminar. Secondary electrons and backscattered electrons, both of them are used for imaging. And also X-rays, including continuum X-ray and characteristic X-ray. Characteristic X-ray is a signal used for elemental analysis. And also light, including ultraviolet, visible, and infrared. These are the signals used for cathodoluminescence. There is also heat generated in the interaction, as well as the specimen current used for EBIC. So the most commonly used signals by SEM are the secondary electrons, backscattered electrons for imaging, and characteristic X-ray for composition analysis. These three can be found on most SEMs. Secondary electrons are the electrons generated during the interaction of the incident electron beam with the specimen. They are called secondary because they are not the primary beam electrons. Secondary electrons have very low energy. By arbitrary definition, their energy is smaller than 50 eV. Backscattered electrons are the primary beam electrons when they are scattered back out of the specimen. The energy distribution of backscattered electrons is very wide. There is a peak near the incident beam energy E0. These electrons are from elastic scattering. There is also a continuum of backscattered electrons. These electrons are from inelastic scattering. Interaction volume is the volume inside the specimen in which interactions occur while being stuck with an electron beam. Interaction volume depends on two factors. Beam energy. The electrons with higher energies will penetrate deeper, therefore lead to larger interaction volume. Specimen composition and density, or average atomic number. The electrons will more likely to be stopped if the specimen material has heavy elements and is denser. Therefore, the higher Z, the smaller the interaction volume. There is an even more important concept, effective generation volume. It is called effective because only the signals generated inside this volume will be able to escape from the specimen surface and be detected, therefore contribute to the image. It is important since it limits the spatial resolution directly. Different signals have different effective generation volumes, depending on the energy the signal carries. Now let's take a look. The secondary electron effective generation volume is very small. Since secondary electrons are low energy electrons, they won't be able to travel from very deep in the sample to the surface. Backscattered electrons have a much larger effective generation volume because backscattered electrons have much higher energy. They can be backscattered out of the sample surface from much deeper in the sample. characteristic X-rays are more powerful than electrons. They may even escape from up to full interaction volume depending on its energy. Fluorescent X-rays are generated even outside the interaction volume. The spatial resolution is limited by the corresponding effective generation volume. Spatial resolution is limited by effective generation volume, which is the reason sometimes we need to do Monte-Carlo simulation. It simulates the electron trajectory in solids. Therefore, we are able to get information on the interaction volume and the effective generation volume. This is a Monte-Carlo simulation of 15 keV electron trajectory inside 4 different materials, from light element carbon to heavy elements tungsten. We can see that the interaction volume decreases quickly as atomic number increases. Here is the simulation of the effect of beam energy on the interaction volume: 5 keV, 15 keV, and 25 keV. The interaction volume increases dramatically when beam energy increases from 5 keV to 25 keV. Simulation can help us to determine the lateral and depth resolution for a particular signal in a defined sample. It is very useful too for testing whether a measurement is possible or for interpreting the results. Now let's move to the next topic: secondary electron detection and imaging. Secondary electrons are generated by the incident primary beam electrons. There are 3 types of secondary electrons. SE1 is generated right after the incident beam electrons entering the sample surface. SE2 are generated right before backscattered electrons exit the sample surface. Here we can see clearly why the spatial resolution is not only dependent on the incident beam size. We can imagine that if only SE1s are collected by the detector, the image resolution will be much better. But unfortunately, it is impossible to separate SE1 from SE2. So SE3s are generated after the backscattered electrons exit the sample. These backscattered electrons will hit somewhere inside the chamber, such as pole piece or specimen chamber wall. So SE3, these secondary electrons are not from the sample itself. Secondary electron detectors. The conventional type is called Everhart-Thornley detector, ET detector, which is located at the side of the specimen chamber. The construction of an ET detector. First, there is a Faraday cage, also called a collector, which is a few hundred volts positively biased so that only low kinetic energy secondary electrons will be attracted. Behind the Faraday cage, there is a scintillator, which is positively biased 10 keV to accelerate the electrons collected by the Faraday cage so that they can efficiently excite the scintillating material. And there is an amplifier, which amplifies the signal. This is a typical image by ET detector, electro-deposited gold dendritic structure. We will discuss in the next few slides that the contrast of the image acquired by ET detector is not only from secondary electrons. There are other factors that are contributing to the image contrast. For example, backscattered electrons. As a matter of fact, ET detector detects not only SE1 but also BSE directly when the BSEs are scattering towards the ET detector, and indirectly through SE2 and SE3. Since both SE2 and SE3s are generated by backscattered electrons. So therefore, backscattered electrons also contribute to the image acquired by ET detector, but it will degrade the spatial resolution. This is a typical secondary electron image with spheres of different sizes sitting on a surface. The main reason that the secondary electron imaging can provide us topographic morphology information about the sample surface is that the secondary electron yield is strongly dependent on the relative orientation of the incident beam and the sample surface. As we discussed earlier, an important consequence of the low energy of secondary electron is that they have very shallow escape depths. When the angle between the incident beam and the surface normal is zero, only the secondary electrons generated within the distance r0 of the surface will be able to escape and detected. When the surface tilted an angle theta, so now instead of r0, the secondary electrons generated within the depth of r can also be detected, since the electrons can take the path of r0 instead of r. And r is proportional to r0 with a proportionality constant secant theta. Therefore, the relationship between the secondary electron yield and the angle between the surface normal and the incident beam can be estimated by this equation. So we can see that when the theta equals to 0, the incident beam is parallel to the surface normal and the yield is the lowest. When the theta approaches to 90 degrees, where the incident beam is perpendicular to the surface normal, then the yield is the highest. And this is clearly demonstrated in this image. The sides of the spheres are brighter as a result of a higher secondary electron yield. This is why we have edge brightening effect in secondary electron imaging. Near the edge, more electrons can escape from the surface to be detected. The edge brightening effect also depends on the accelerating voltage used. We can see clearly that the effect is more significant in the 30 kV beam image than that in 1 kV beam image. Modern SEMs also use through-the-lens detectors, which are sometimes also called immersion lens detector or upper detectors, like in our two Hitachi SEMs. Unlike ET detectors, this type of detector is located inside the electron column, inside the objective lens. This type of detector is often used in so-called immersion mode, where objective lens projects a very strong magnetic field on the sample. With the help of this magnetic field, SE1 and SE2s are collected with high efficiency, since secondary electrons, mainly SE1 and SE2, are trapped by this magnetic field and spiral upward around the lines of magnetic flux to the detector above the lens. Since SE1s are generated by direct interaction with the incident electron beam, they carry highest spatial resolution information. And with this through-the-lens detector, BSE and SE3s are excluded because The highly energetic backscatter electrons are less strongly confined by the magnetic field and do not reach the detector. Also, SE3s are generated inside the vacuum chamber. It's very far off the optical axis. Therefore, they won't be affected by the on-axis magnetic field. While SE1 and SE2s are efficiently captured by TLD through the lens detector, the BSE and SE3 collection by the ET detector is relatively unaffected. So which detector should we use, ETD or TLD? First, these two types of detectors are located in different places inside the SEM, so they see the sample differently, therefore affects the image appearance. ETD is located at the side of the specimen chamber, therefore it sees the sample from the side. So there is always a shadowing effect in the electron collection, since the electrons emitted towards the ETD are more likely to be collected than those traveling away from the detector. This is an image of an indent. Because of this shadowing effect, the face looking away from the ETD appears dark. TLD is located up inside the objective lens. It sees the sample from above. Regardless where these secondary electrons are generated, inside the magnetic field, they all spiral up the poppies. So the secondary electron collection by TLD is symmetric. There is no shadowing effect, which is a reason in this image by TLD, all faces of the indent are equally visible. The signals these two types of detectors collect are also different. TLD collects SE1 and SE2 only because only SE1 and SE2 are confined by the magnetic field. As for ETD, when the immersion mode is on, SE1 and SE2 are now pulled up by the magnetic field. The signals collected by ETD are mainly BSE and SE3. We can see that the image taken with TLD gives more surface details, since SE1 carries the highest spatial resolution information. And these details are not visible in the image taken by ETD. Also, the image from ETD usually carries more material contrast information than the image taken by TLD, due to a much higher percentage of backscattered electron collection. And I will show you later in the presentation that BSE, backscattered electron yield, is strongly dependent on the atomic number of the material. And this is not demonstrated in this set of images, since these are gold particles and there is no composition difference. As we discussed in the last slide, through the lens detector can efficiently collect SE1 and SE2, with BSE and SE3 excluded, therefore gives high surface resolution imaging. However, more advanced through the lens detectors can also detect BSE, although the detection is indirect through SE3. This is done by adding BSE conversion plates and secondary electron control electrodes inside the objective lens. The BSE conversion plates are designed to convert BSE to SE3. The arrangement of these biased electrodes and BSE conversion plates allows us to select the energy range of the detected electrons, which means we now can choose what electrons are going to be collected by the through the lens detector and contributing to the image. To explain it in a simple way, this is how it works. When the electrode is positively biased, OSE1 and SE2 are going to the through the lens detector, providing ultra-high surface resolution imaging. But when the electrode is negatively biased, SE1 and SE2 are now going to be rejected from the pupils. Therefore, they won't be detected by the through the lens detector. The signals for through the lens detector are now from BSE, to be exact SE3, which are converted from BSE. The system can be adjusted to give images of pure SE to pure BSE and anywhere in between. Detection of BSE by through the lens detector allows us to get high resolution imaging with compositional contrast. As we will discuss later in this presentation, the BSE yield is strongly dependent on atomic number, and therefore BSE imaging gives compositional contrast. This also provides us the flexibility in overcoming charging effect, since backscattered electron imaging is less affected by charging. Negative bias can also be applied to the sample, to the stage, to decelerate the incident beam, therefore improve the low voltage performance. There is a standard working distance where both detectors can have a reasonable signal level. A smaller working distance will give a stronger signal for through the lens detector, upper detector, and a better image resolution, but a much weaker or even no signal for lower detector due to the shadowing effect. A longer working distance gives a stronger signal for the lower detector. It also allows more room for sample tilt and greater depth of focus. So for higher surface resolution, you might want to use upper detector through the lens detector combined with a shorter working distance. For a better three-dimensional illustration of the feature, you might want to use lower detector, ET detector, combined with a longer working distance, as clearly shown in this set of images. While SEM image appears to be three-dimensional, since it gives a very good three-dimensional impression of the feature, it actually contains no depth information. Therefore, it is two-dimensional, 2D. Sometimes the perception of the feature can be deceiving. Like the image shown here, it might be hard to tell whether these features are bumps or dimples. To get a real shape of the feature, we need 3D SEM. Now let's move to the next topic, backscattered electron imaging and its detectors. Backscattered electrons are the primary beam electrons that are scattered back out of the sample. So how to interpret a backscattered electron image? Again, the major contribution to the image contrast comes from electron yield. In this case, backscattered electron yield. The backscattered electron yield increases monotonically with average atomic number of the specimen. Therefore, backscattered electron imaging can give compositional contrast. This is most useful on multi-phase samples. This set of images were taken from the same area. The upper one is secondary electron image. The lower one is backscattered electron image. We can see that the contrasts are completely different in these two images. The grains appear to be bright in backscatter electron image because they are lanthanum-rich phase, which has a much higher average atomic number. Compositional contrast sensitivity in backscattered electron imaging can be as high as 0.1 average Z differences. But please be aware the surface topography also affects the backscattered electron collection. Therefore, a flat, polished specimen is critical for best sensitivity in compositional mode. Backscattered electron detectors are mostly solid electron detectors. It is placed annular to the bottom of the objective lens. Often it has 4 quadrants. The scintillator type detector is also available. There are 2 types of backscattered electron imaging. One is BSE compositional imaging, which is obtained by electronically summing signals from all 4 quadrants. The other is BSE topographic imaging, which is obtained by differencing various detector quadrants. Switching between these 2 modes is easy through the software control. Backscattered detector can also provide us electron channeling contrast, which gives us crystallographic orientation information in suitable samples. A comparison of the images taken using different detectors or image modes. Secondary electron image, backscattered electron compositional image, and backscattered electron topographic image. More examples of backscattered electron compositional contrast. These 2 are secondary electron images, showing only the surface morphology. The buried phase are not visible. These 2 are backscattered electron compositional images, where we can see these buried phases. The next topic is the effect of major beam parameters on imaging. As we discussed earlier, there are several electron beam parameters which the operator has control. It is very important for the operator to optimize the probe condition to get the best result. These parameters are a probe diameter, probe current, probe convergence angle, and accelerating voltage. In the next few slides, we will show how these beam parameters will affect the image quality. Probe size and probe current. First, for the same electron source, the probe current increases monotonically with probe size. When the probe size or current gets smaller, we will get a higher resolution image owing to a smaller interaction volume. We will have a smaller specimen damage, but the image will appear rougher due to a poor signal-noise ratio. When the probe size current gets bigger, we will get a lower resolution image as a result of a bigger interaction volume. We will have a larger specimen damage, but the image will appear smoother owing to a higher signal-noise ratio. These 3 images were taken using different probe sizes, probe currents. We can see that the best image was taken using 20 nanometer probe and 5 picoamps current. The image taken with 15 nanometer probe, 1 picoamps current is too noisy. And the surface details were obviously lost in the image taken using 130 nanometer probe and 320 picoamp current. Beam energy is determined by accelerating voltage used. The higher accelerating voltage, the higher beam energy. A higher accelerating voltage leads to a larger interaction volume. The interaction volume in purple color is induced by a higher energy beam. It is much larger than the volume in blue color, which is induced by low energy beam. And this is true in both low atomic number material on the left and high atomic number material on the right. A larger interaction volume means more backscattered electrons, therefore more Se2 and Se3s, which means a poor contrast for surface fine structure. So the surface spatial resolution is reduced as the accelerating voltage increases. At the same time, the image will carry more information from deeper in the specimen for a higher energy beam. Also, it will be more likely to be charged, and there will be a larger specimen damage. Let's take a look at this set of images taken at different accelerating voltages, therefore different beam energies. 1 kV, 3 kV, 5 kV, and 15 kV. The sample is a mixture of gold particles and gold plates. In the image taken at 1 kV, we can see surface details of the gold plates. As the voltage increases to 3 kV, some gold plates start to appear transparent to the degree that we can see the gold particles underneath. As the voltage further increases to 5 kV, this transparency becomes more obvious. At 15 kV image, almost all the gold plates in the image look transparent. The gold particles underneath the gold plates are clearly seen. Meanwhile, the details of the gold plate surface are lost. Another good example of the effect of accelerating voltage on imaging. This is a pipette filled with gold. The 3 kV image shows excellent surface fine structures of the pipette. The 15 kV image clearly shows the internal structure, which is a gold core in this case. Let's move to the next topic, charging in non-conductive specimens and what to do. Charge balance in conductive samples. For a conductive sample, incident electron beam interacts with the sample. There will be secondary electrons escaping from the sample surface. There will be also backscattered electrons coming out of the sample surface. The sample current, ISC, is the difference between incoming and outgoing currents. Since the sample is conductive material, ISC can easily flow to ground through the stage, so charge balance is easily reached in a conductive sample. But what if the charge balance is not reached? Electrons will be accumulated, forming electrical field, which will influence the electron signals and therefore deteriorate the image. The typical solutions for non-conductive samples. The traditional method is to coat the sample surface with a few nanometers of conducting material such as gold palladium or carbon, so that the specimen current ISC can still flow to ground through this conducting layer. But be careful, coating the surface with conductive material might modify the morphology. we can see from this image, gold palladium coating has introduced a thin layer of particles, which is visible at this ultra-high magnification image. This is a schematic illustration of the total emitted electron coefficient, including secondary electrons and backscattered electrons, as a function of beam energy. We can see that there are two beam energies where this coefficient equals to 1, which means the amount of incoming and outgoing electrons are equal to each other. And we choose to operate the microscope at E2. This way, the specimen current ISC is 0. Then no conducting pathway is needed. This table lists the values of E2 for several materials. We can see that E2 values are quite small, which means low voltage imaging is required. These two images were taken at different voltages, 10 kV and 1 kV. We can see that in the 10 kV image, there is a charge built up, which affects the image. And the image taken at 1 kV does not have this problem. Another solution is to use a special type of SEM, the one we introduced in the beginning of this seminar, variable pressure, low vacuum, or environmental SEM. The mechanism here is, in the low vacuum mode, gas is introduced into the specimen chamber. The high energy electrons ionize the gas. The positive ions generated are available to dynamically neutralize any negative charge on the sample. This image mode is available in both Schottky source microscope and semionic source microscope. Here we can see this low vacuum mode does work well in minimizing the charging. The left image was taken in high vacuum. We can see that the charging effect is obvious. The right one was taken in low vacuum mode, 20 Pascal air. The charge is effectively neutralized. But there is also limitation using this low vacuum mode. That is, you won't be able to get high resolution image. In the next few slides, we will briefly introduce a few analysis techniques, such as characteristic X-ray for composition analysis, electron backscattered diffraction for crystallography study, and cathodoluminescence for optical and electronic property analysis. Energy-Dispersive spectroscopy EDS is the most commonly used compositional analysis technique in SEM. So how the X-ray is generated in SEM? The incident electrons get decelerated due to the electromagnetic field of the atomic nuclei. So there is energy that needs to be released. Here, the energy from the deceleration is released in the form of X-ray. We call this type of X-ray continuum X-ray. The second type of X-ray generated from the interaction is characteristic X-ray. Here, the incident electrons knock out the inner shell electrons, leaving holes, vacancies behind. Electrons in the outer shells come to the inner shells to fill the holes, since inner shells have lower energies. So again, the energy difference between the inner shell and outer shell needs to be released. One way to release this energy is to generate characteristic X-ray. The other way is to generate OJ electrons, which we are not going to cover in this seminar. The EDS spectrum looks like this. The blue background is from continuum X-ray, and characteristic X-ray form these red peaks, which are superimposed on the background and can be used to identify the elements and for further composition analysis. Using EDS, we can do qualitative elemental analysis from a point or an area. Elements that can be detected are from beryllium up on periodic table. The sensitivity can be smaller than 0.1 weight percentage, depending on the matrix and composition. We can also do quantitative analysis, although there are many requirements and limitations. Also, we can do spectrum imaging, area elemental mapping, and line scans. The spatial resolution of EDS varies from several cubic micrometers to smaller than 1 cubic micrometer, depending on the accelerating voltage used, the element being analyzed, and the matrix. The energy resolution is not very high for EDS, over 100 electron volts, so there might be overlapping issues for some elements. Electron backscattered diffraction (EBSD) technique is used to determine crystallography orientation down to a 5 to 10 nanometer scale. The electron beam is scanning in a rest pattern across a defined area on a tilted sample. Backscattered electrons emitted from the sample surface. The diffracted electrons will form Kikuchi pattern on a fluorescent screen. Since the pattern is characteristic of the crystal structure and orientation in the sample region where it is generated, so the pattern can be used to determine the crystal orientation. Therefore, we are able to get a corresponding crystal orientation map. By analyzing the EBSD data, we can get information such as grain size and shape distribution, local misorientation, misorientations between grains, and phase distribution, and local strain. Cathode luminescence is used for optical and electronic property analysis. The electron beam is scanning in a rest pattern on a luminescent material. Then light of different wavelengths may be emitted by irradiation of the energetic electron beam. Then the CL cathodoluminescence response is recorded from the CL detector. Then the CL image can be generated. This is a panchromatic CL image of gallium nitride. These dark lines are obviously due to reduced emissions and correlated to defects such as dislocations. MRL has GOL 7000F, which is an advanced analytical SEM. With GOL 7000F, all the techniques we discussed earlier are available. We can do both EDS and WDS for composition analysis. We can do cathodoluminescence for optical and electronic property analysis. We can also do electron backscattered diffraction for crystallographic analysis. Safety and awareness when using SEM. First, the microscope alignment is critical for getting good image. The alignment usually starts with gong or beam alignment. We want to make sure the beam goes straight down along the electron optical axis. Aperture alignment is also important. We need to make sure the aperture is centered along the optical axis. So what if these two are misaligned? We will see features moving when we are focusing. We need a stigmator to correct astigmatism, so the stigmator also needs to be aligned. What if the stigmator is misaligned? We will also see feature moving, but this time is when we are correcting astigmatism. Please be aware, a strong magnetic field is projected on the stage from the pole piece, especially in ultra-high resolution mode, which in some microscopes is also called immersion mode. Therefore, we cannot work with ferromagnetic powder, and we cannot work with ferromagnetic bulk samples unless they are firmly attached to the holder. For your information, the AFM discs are strong ferromagnetic, so please remove it before you start your SEM session. Also, you cannot use ultra-high resolution mode or immersion mode for ferromagnetic bulk sample, even it is firmly attached to the stage, since the magnetic field is much stronger in ultra-high resolution mode. Otherwise, this is what will happen. The sample will be attracted to the pole piece. As shown in these two pictures, which were taken after this kind of accident happened to our SEMs. This not only might damage the pole piece, degrading the resolution, the powder sucked into the pole piece can even kill the microscope. We have put a magnet near the sample loading area in the lab, so if you are not sure about the material you are working with, please use the magnet to test. Fail to follow these rules will result in suspension of your microscope access. During the operation, we also needed to be very careful. Please do not bump the pole piece when lifting and tilting the sample. Please watch the chamber scope when lifting or tilting the stage. Always keep a safe distance away from the pole piece. Never allow any part of the specimen or stage to touch the pole piece. Otherwise, the pole piece can be damaged. This is a picture taken in Hitachi S4800. The pole piece is viewed from the bottom. We can see that the pole piece was scratched badly. These scratches affect the electrical field distribution, which has degraded the resolution to a certain degree. Again, fail to follow these rules will result in suspension of your microscope access. Finally, we will briefly introduce the SEMs available at MRL. In this section, we will briefly introduce SEMs in MRL. GOL 6060LV and Hitachi S4700 are the two SEMs open for new users. GOL 6060LV has thermionic tungsten source. The resolution is roughly 10 nanometer, and it is excellent for large features. And since the electron source is tungsten, it gives large current for EDS analysis. It has a backscatter detector, and it can be operated at low vacuum mode, up to 2 torr. The low vacuum mode is useful for non-coatable samples and samples that are not high vacuum compatible. So if you are working with this kind of samples, GOL 6060LV will be your microscope. Hitachi S4700 has cold field emission source. The resolution is roughly 2 to 3 nanometer. It is good for sharp imaging of nanoscale features such as particles and samples with fine surface detail. It has EDS detector and backscattered detector as well. Hitachi S4800 is a newer version of Hitachi S4700. It is better in the way that it has better high-resolution low-voltage imaging, 1.0 nanometer resolution at 15 kV, 1.4 nanometer resolution at 1 kV. It has beam deceleration mode for shallow surface topography. It has controlled signal mixing, combination of secondary electron and backscattered electron. It can obtain pure BSE imaging at low voltages, which means compositional contrast imaging with better spatial resolution. GOL 7000F is our advanced analytical SEM, equipped with not only EDS but also WDS, EBSD, CL detectors. With GOL 7000F, in addition to surface topography morphology, we can also study crystallography, optical, and electronic properties of the material. Here is a list of references for this presentation and the additional resources where you can find more information about SEM and its related characterization techniques. The microscope rooms will be closed and locked on weekends, university holidays, and between 5:30 p.m. and 8:30 a.m. on weekdays. To have off-hour microscope access or room access, you need to complete BEEP training, Building Emergency Action Plan training first. And you will also need to finish at least 10 hours self-use sessions on the instrument. And then you can request key at mymrlillinois.edu. Please make sure you have room access before booking off-hour sessions. You now have finished MRL SEM orientation video. Congratulations. So what's next? Please go to the Compass 2G website to sign up for MRL SEM orientation and take a short quiz. You will be contacted by the SEM staff once the instrument group training is scheduled for you. If you are interested in becoming a SEM user at MRL but have not submitted the training request, please submit the training request first so that we can have you on our training waiting list.